Hello, my name is Deniss. I'm a PhD student and researcher from Riga Technical University. I would like to present our study, Prospects of Structural Damage Identification using Modal Analysis and Anomaly Detection. There are structures which require its health monitoring to ensure they work properly and without risk of failure. Structures like wind turbines and aircraft parts are remote and cannot be conveniently stopped for conventional non-destructive testing procedures. As a solution, operational model analysis is used for obtaining model parameters which directly represent the state of the structure. Composite materials are frequently used in these applications, and timely damage detection is essential both in terms of safety and maintenance costs. The goal of this study is to detect a damage state for a finite element model of a composite beam structure using machine learning method called anomaly detection. The beam is 1 meter long, 10 centimeters wide and 2 millimeters thick, and is made of carbon fiber reinforced polymer. Later we introduce damage, which will be delimitation. First, model analysis of the finite element model is made. 5 modes are calculated, which have the following frequencies and shapes. As mode shapes have quite a large amount of elements, these are normalized and approximated with smaller amount of points for better computation, using 12th degree polynomial. Mode shapes are two-dimensional, having x and y direction, while z direction along the axis doesn't change its value. For anomaly detection algorithm, we needed a set of healthy states which slightly differ from each other in terms of model parameters. This set would be used to teach the algorithm of the healthy state, so that it has a reference to which compare future samples. So 5,000 identical samples were made, and Gaussian noise with a factor of 0.6% was added to this set in random fashion. The standard deviation of model frequencies is shown in this table as an example. Model shapes have similar standard deviation. Damage is introduced into the model as a delimitation between layers 18 and 19, that is 2 layers down from the top. Delimitation is 5% from total beam area. The location of delimitation is slightly shifted around the beam, which is expected to have different effect on modes. Approximated two-dimensional mode shapes are formed into a single vector. Here is the first mode shape, which is the first bending shape. Mode shapes are also normalized to the values from 1 to 2. The noise added to the original mode shape slightly alters the values of each shape point. It is intentionally made with smaller intensity than the damage to test the algorithm for procedure correctness, not for sensitivity. As you can see on the plot, the yellow line shows delimitation at certain points, while the mode shape with noise have random and small perturbations around the healthy state. Healthy state samples are taken and are represented by a vector x, which contains frequency as the first element and then all mode shape points. The probability of each sample is calculated using multivariate Gaussian distribution. This upper plot shows Gaussian distribution of a single variable probability over the frequency axis. Lower graph shows distribution of multivariate probabilities. The damage state is clearly an anomaly here. Number of feature n is 202, which is quite high. This results in very high probability values, which is why they are plotted logarithmically. The threshold is first set at the minimum probability and then increased stepwise. For each threshold value, an F1 score is calculated, which is a better way to measure accuracy. The final threshold is chosen with the best F1 score value. As you can see in the shown example, first 4 thresholds have good accuracy, then the 5th threshold does not, which makes the 4th one the optimal option. To put everything into perspective, here is the block schematic of the anomaly detection algorithm. First, you choose features indicative of anomalous examples. Second, divide data set into training, cross-validation, and testing samples. Training is used to feed mean value and standard deviation parameters. Probability is then calculated for training set, which is marked as healthy reference. Next, cross-validation sample set probability is calculated, where a small amount of damaged samples is present, potentially having significantly different probability. Then threshold is calculated or simply set as a 3 times standard deviation as an example. Finally, use testing set to test the correctness of the algorithm. Conclusions. Algorithm is able to correctly identify both damage states from test samples for modes 1, 2, and 4. Torsional modes, however, that is modes 3 and 5, need reformation of mode shape vectors for correct representation. Multivariate Gaussian distribution is not optimal for a large amount of features because probability values become very high. Alternatively, we can use compressed data to describe mode shapes, for example, modal assurance criterion, that would give one scalar instead of a large vector to describe the state of mode shape. And finally, chosen delimitation has small influence on model parameters and most likely will be masked by noise in a real-world application. But that just means that probably this type of damage is not critical. We would like to thank European Postdoctoral Research Aid for Latvia and Riga Technical University's doctoral grant program for making this study possible. Thank you very much for your attention.